So for the midpoint rules, the errors is order h square, okay? And for the trapezoidal rules, the order h square as well. But for Simpson rules, you can have order h to the fourth, okay? And then, you know, like for Simpson rules, then you have to require the function at least 4 times differentiable. And I show you the MATLAB, how to implement the quadrature rule. So for this MATLAB function, you can use to implement the Simpson rules with step size h, okay? And we use this formula. So Simpson rules is 2/3, midpoint rules plus 1/3 trapezoidal rules, yeah? And we did some numerical example. And then I show you that, you know, from this example, you can derive what is the order of convergence numerically, okay? By taking the errors table, plug it in this formula, and you get some order of convergence row. And here, if you doing that for the previous table, you can see the midpoint rules, the order of convergence is 2. So the theory is consistent with the numerical experiments, yeah? So in the project, I will ask you to do the same, yeah? So you will produce a table of errors like this, and from the errors of tables, you deduce the order of convergence numerically, okay? Not theoretically, yeah? So now, today we cover the very last topic of quadrature. So you see, so Newton are very smart, right? I mean, he say that give me m point quadrature. I can compute the quadrature not exact for polynomial degree m, okay? But Gauss say that I can do better than Newton. Well, okay, why? Because he said that it is possible to make the degree of precision is higher, 2m minus 1, yeah? So see Newton, if you plug in a polynomial of degree m, okay, then its integral is exact with a numerical integration. But if you put something of degree m plus 1, then the error is non-zero, okay? But Gauss said that I can do better. If you plug in a polynomial of degree 2m minus 1, the rules is still exact. So what is the invention of Gauss? Well, he said that, okay, so for Newton rules, first you choose the point equally spaced. Then after that, you design the weights. Yeah? So you design the weights by integral of the Lagrangian, right, based on the points. But Gauss said that, you know, why don't we choose the point and the weights simultaneously? You know, you let them free. Yeah? So here, the points are predetermined. And then after that, you compute the weights. But here, the points and the weights are free. And by that, you can increase the degree of precision to 2m minus 1. Yeah? So the theory is a bit complicated. So we are not going into details, but I'm going to present only the simplest case. So the simplest case is, well, first, before we discuss the theory, let's move the interval back to minus 1 to 1. Okay, so but if you have an interval from A to B, you can make a linear transformation and map it back to minus 1 to 1. Yeah, so we can do this easily. So suppose now, you know, you want to find a Gaussian rules for integral from minus 1 to 1, and the degree of precision is 3. Yeah, so remember m is 2, which means that you have only 2 points. Yeah, for Gauss rules, then the degree of precision is only maximal is only 2, right? Can be 1 or can be 2. Yeah, but Gauss rules say that, you know, I mean, the degree of precision can be 3. Okay, 2m minus 1 is 3 in this case. And how does he do that? Well, now what does it mean by the integral exact for polynomial of degree 3? Sorry, for polynomial up to degree 3, yeah? It means that if you take the function 1, yeah, you integral it, And it should be the same as the quadrature applied to the function 1. Okay, so you apply the quadrature to function 1, so it means 1 here, time weight 1, time weight 2. Okay? And similarly, suppose I apply the integral of the function x, then, the quadrature when you apply function x is f of x1 just equal x1, f of x2 equal x2, okay? And so on. So you go from degree 0 to degree 3. So degree 3 is x3. And then you have w1, w2, x1, and x2. So you have 4 unknowns. Remember, we allow the weights and the point are free. So now you have 4 unknowns, the weights, 2 weights, and the 2 unknowns quadrature points. But you have 4 equations, yeah? 4 unknowns. So solvable. Well, in this case, that you can find out the system has, and it's non-linear, yeah? So the system is not easy to solve. But Gauss said that I can solve it easily. So solution is just the weights are 1 and 1, W1 and W2 equal 1, and the quadrature point is x1 and x2 are just symmetric with respect to the origin. And the absolute value is just 1 over square root 3. And you can see that they satisfy those conditions, because this integral is just equal 0, right? Sorry, this integral equal 2, yeah? Because you integral 1 from -1 to 1, just equal 2. So W1, W2 equal 1, so 1 plus 1 equal 2. So that's correct, yeah? And this one is an odd function when you integral from -1 to 1, so it's equal 0, yeah? So you plug it in here. You got minus 1 over root 3 plus 1 over root 3 equals 0. So that's correct, okay? And you can check that, they satisfy those 4 equations. So therefore, this rules integrate exactly all the polynomials of degree less than or equal 3. Yeah? And we can summarize, the Gauss rules for 2 points like this. So you take an integral of f from -1 to 1. It approximates by the value of the function at -1 root 3 plus 1 over root 3. And, we show that it has degree of precision 3, yeah? And then the errors will be depends up to the 4th derivative, yeah, of the function. And so suppose you take this function, you compute, the integral by 3 methods. The composite-Jordan rules, yeah? So are 2 minutes. Simpson rules, okay? And then you compare with the Gauss rules. You will see that the Gaussian rules is more accurate, okay? So now in general, you can have an n-point Gauss-Legendre rule, yeah? And, the quadrature point can have a different name. They call it abscissas. And then, the errors will be of this form. So it will be exponential decay when the number of n go to infinity. So see before, you have the quadrature depends on h, the step size, yeah? But here, because the quadrature points are not evenly spaced, are not uniformly distributed like before. So actually now the errors depends on number of points, and it decays exponentially. Okay, so we are not going to prove this. So, and we are not going to give, the formula for all the quadrature points because it takes a bit more theory, and we don't have time. But if you're interested, you can look it up on the internet. So essentially, we have to define what is the Legendre polynomials, and then how you find the zeros of Legendre polynomials, and then those will be the Gauss point, yeah? And for example, for n equal 2, 3, and 4, those points are given like this. It looks terrible, but actually it could be nicer like this. Yeah, so you see for n equal 2, you have that plus and minus 1 over root 3. And then n equal 3, symmetric over the origin. You have an origin here. And you have plus and minus this number. And the weights, see the weights are not equally everywhere. See, the weight here is 5 over 9 at those points and 8 over 9 at the middle. And then n equal 4 and so on. You know, so we are not going to the general theory, but that is the Gauss-Legendre rules. Yeah. So now, back to the integrals over the intervals a and b. So you see, how do we map it to minus 1 and 1? Well, just use this chain of variable. And you can see that if I put t equal minus 1, yeah? If I put x equal minus 1, then what do I get? If I put x equal minus 1, then you just got a, right? Yeah? And if you put x equal 1, you just get b. Okay, so this map the intervals a, b into minus 1 and 1. Yeah? And then your integral, okay, will be transferred from a to b to minus 1 to 1. And you just apply the Gauss rules for this. Yeah? So this one, where do we get this one? Because dt equal b minus a over 2 dx. Yeah, so that is how you get these extra terms. Yeah. And you see now if you have the Gauss rules for the minus 1 plus 1, then you apply that to this function, then you approximate the integral from a to b. So integral from a to b is not a problem. Yeah. So as long as you have the integral from minus 1 to 1, then it's okay. So now look at this example. So now suppose I have some program that it run, through different cases. Okay, and you can see that for the trapezoidal rules, I have this results. Yeah, this is the value and this is the errors. And then I compute the order of conversion at about 1.5. Yeah? And then I use Simpson rules. Then I run through it, and then it gives me order 1.5 as well. But the theory says that Simpson rules can have order 4. Yeah? So what's wrong? So what's wrong with this example? And the trapezoidal rules, you can have order 2, right? Yeah, remember? So we said that trapezoidal rules, you can have all s squared, yeah, the order of conversion. But here, I just have only 1.49, yeah? And then I use Simpson rules. The situation is still the same. Does it get better? The order of conversion is only 1.49. So why is that? So what's go wrong? What went wrong? Huh? Derivatives. Correct, yeah, because if you take the derivative of this, what do you get? You get 1 over 2 square root x, yeah? And 1 over 2 square root x blows up at 0. See, your theory says that you have to be at least C2 in order to have order conversion 2 for trapezoidal rules, yeah? And for Simpson rules, you have to have C4, 4 times differentiable. But here, when you take derivative on the first derivative, it blows up at 0. So the theory is not applicable anymore. So you see, sometimes when you see the theory, you have to be very careful about the assumption. under what assumption then you have the results. Otherwise, you cannot use the theory. Okay? So in this case, how do we fix the situation? We can change the variables. So if you change the x equal y square, then integral of square root x become integral of y square. And y square is c infinity, right? So you don't have to worry. Yeah? So then you can apply the quadrature for this. And you still get a good numerical result. And similarly, if you have a function like this, there's a jump here at 1/4, then you can split the integrals into two integrals. And then this one, you use this transformation again and make it, C4, and then you can apply the quadrature. Or suppose you have a lot of oscillation. This function oscillates a lot, sine 50x, and you just put more points. Yeah. So see, this is a square root function, has a cups here, and this one is the square root of x minus 1/4. You have a cups here. You just remove this by split into two integrals. Or you have an oscillation like this, just put a lot of more points here. Okay. And in MATLAB, so there's a few functions that allow you to do the numerical integration. Okay, so this one is one example. So they have a few more. I didn't list the whole list. They have integrals 2 and quad k. But here suppose quad is they just use the Simpson rules. Yeah. And what you have to do is to just define a function anonymously. So this is an anonymous function. And then you pass through the function quad, yeah, and pass the beginning, the left and the right hand side. And sometimes you can pass in the tolerance, like how many digits you want it to compute. Yeah, so then it's very easy to use. Okay, so that is everything about quadrature. So any questions before we finish this topic? Move to the last one. So any question? So somebody found some typos in the lecture notes. I fixed it. So please go to Moodle and get the updated one. Yeah, because there's some wrong calculation. Then I fixed it already. Anyway, yeah. But the theory is still correct, yeah? Only some typo in the integration. So everything is okay, yeah? So we finished this quadrature, yeah? No more question? Everything is clear, yeah? Suppose there's a question about quadrature in the final, then you can do it easily, yeah? Okay, so we move to the last topic. The last topic is initial value problems. And as you can see, the project is just a way for you to study the last chapter. Okay, the project is for you to look ahead into this last topic and implement it. So in the project, you see that you have to implement Euler methods, you have to implement Ronch-Cutter methods, and you have to use the MATLAB already solvers. Okay, so more or less at the beginning and the end of the topics. Yeah. So now, what is initial value problems? Well, so we just look at some example. So again, we see Newton again. See, so Newton, he knows everything. So Newton law. Yeah. So Newton law, he say that suppose that you have a body and it's cooling down, yeah? Then T is the temperature, okay? Then the rate of change of the temperature with respect to time is proportional to the difference between the, the medium temperature, yeah? So the rate of change of the temperature is just a constant time, the difference of the temperature of the body minus the temperature of the the ambient, the medium. And this is the ODE, right? Ordinary differential equation, because you see these are unknown. So these on the left appear the first derivative with respect to time, and t appear on the right as well. So it's called ordinary differential equations. And when you have some initial condition, when time equals 0, you know that t will be something, yeah? Then it's called initial value problems, okay? And another example is when you drop something, you know, from, say, from the level 15 of the library, yeah, you drop something, drop a book there. Well, actually, you cannot do that because it's totally closed, yeah. But anyway, so the object will follow this equation. This is acceleration, yeah, just equal the gravity constant. So more or less, it's a Newton law, yeah. So F equal ma. So acceleration is just equal the gravity in this case because fallen down by gravity. And you can see that, you know, the s is unknown, and there's a second derivative here. So ordinary differential equation as well, of order 2. Okay, so order is the highest derivative you can get. And we have to assume some initial conditions. So when time equals 0, yeah, maybe the height is the level 15 of the library. Okay, and you have to assume some velocity, you know, because sometimes people throw something from the from the building, you know, so you have some initial velocity, yeah. Then it will completely determine the motion of the object when falling down. And so this one is the system that you see from your project, okay? So Edward Lorenz, he's an American mathematician. And he's not a mathematician, I think he's some scientist, forgot. But anyway, so it's very recent. So 1963, not very long time ago, right? And so when he tried to model the atmospheric flow, then, you know, there was a very complicated equations, but it just simplified into this system of 3 ODE. And you can see that on the left, you have x, y, and z unknowns, yeah? And you take the derivative with respect to time. And on the right, you know, you have x, y, and z unknowns as well, yeah? And now this one becomes famous, that they name this equation is Lorentz equations, yeah? And you will see that by choosing some different sigma, rho, and beta, it will have some different properties of the solution, you know, and it has some attractors. So maybe let me show you a movie. Yeah, so there's a name for the Lorentz attractor. So somebody solved this system of ODE already, and now he just plotted. So what it is he just plot the solution in x, y, and z, and x, y, and z is a point in space, yeah? And he tracked through time. So when he tracked through time, then it just become a curve. Just forget about the sphere, you know, just look at the big curve, yeah? And now he just do the animation. And see, you see that this is time equals 0, and then, you know, time move on, then you see that the solution traced through space, and it become a Lorentz curve like this. So, you know, in your project, I don't expect you to give a fascinating animation like this, but you should be able to plot some curve like this in 3D. Okay, so you plot 3 command in MATLAB, you should be able to plot something like that. And I don't want you to put music in, the animation, so you don't have to. So, but you see, this is the attractor. You see this one, when as time goes by, you see that the solution got attracted into 2 points, and they call it Lorentz attractors. Okay, and see, so it looks like this. So you see, I mean, I don't expect you to have a nice pictures like this, but at least it looks close. When you plot it, you will see that you should see some spiral like this. Otherwise, there's something wrong with your program. Okay? And you can see that in the end, he said that everything was made by Euler method. 5,000 iteration, Euler methods, with step size 0.01. Okay? So your first task is Euler method, explicit Euler method to implement this. Okay? And then after that, you use Ronne-Scudder method, order 4, and implicit Ronne-Scudder method for order 4. Okay? And I can show you that, for the first 2 tasks, everyone can do it. And you can look up on Google. There's a lot of samples there as well. But for the last one, even if you look on Google, there's none. So try the last one. The last one is the implicit Ronne-Scudder method. Yeah, and so that is about the project. You still have 4 weeks or 3. Well, because you see, I realized that the last lab is Anzac Day, so it means that you should have an extra week for that. Yeah. So if your lab is on Thursday, it means that it will be the last one will be Anzac Day, so you have an extra week. So how about if your lab on Wednesday? So it's up to you. I think I can extend it to the next week as well. So roughly you have like 4 or 5 weeks to do this. Yeah, so plenty of time. Okay, yeah. Okay, so now go back to the theory. So the theory is, so suppose you have an ODE like this, yeah? So ODE, on the left you have just a derivative with respect to time, and here y just a, one dimensional, just a single function. On the right, you have a function that can depend on y and t is for time, yeah? And you have some initial condition, okay? Initial condition is when time equals 0. Then we call it the initial value problem. So now, the question is whether you have a solution or when do you have a solution for this. And we are not going to prove it, but at least we should know that there's some condition. Okay? There's some condition for you so that the system, the initial value problem has a solution. So we assume that the function is continuous in 2 variables. Yeah, the function f. And further than that, you assume that the function is bounded over a region. Yeah, so we can discuss it a bit more, yeah. And then we can assume that the function is Lipschitz in the sense that if you take the difference, okay, of f evaluated y1 minus f evaluated y2, then it's controllable by some constant time, the distance between y1 and y2. Okay, for some region. So this condition will be automatically satisfied if f is continuously differentiable, because the mean value theorem say that this difference is just partial f at y at some point y in the middle, and if it's bounded, then definitely you have this condition. Okay, so you just make this one absolute value and less than or equal L times the absolute value L y1 minus y2. Okay, and Lipschitz. Then under those assumptions, then the initial value problem has a unique solution. okay, for some point in time. So we are not going to prove it, but at least we know that under a certain assumption that the initial value problem has a solution. Because otherwise you can run into the problem like this. Suppose the theory says that there's no solution, but you still have a numerical solution. So then your numerical solution contradicts the theory. Yeah? So here we say that, okay, by theory that there is some solution already. And then from the numerical algorithms, we give the solution, okay, approximate solution. So for example, suppose I take this function, this ODE, yeah? Then, so what is the, so what is the assumption? So you see that dy over dt, yeah? Focus. No? Okay. So dy over dt is 1 plus y squared. So you see that f on the right hand side is 1 plus y squared, right? Okay. And you see that this one, if you plot it in, say this one is t and this one is y, right? Then this function is continuous because they have no t, so it's continuous. Continuous on any region. Continuous in two variables, yeah? So in any region, y, so y min, y max. So this one is any region, yeah? So this one, suppose this one is y min, and this one is y max. And this one is 0, and this one is t, yeah? So then it satisfies the condition. And how about partial f with respect to y? So partial f with respect to y just to y, yeah? And this one is bounded when you restrict y into this region. So bounded just by y max, yeah? So therefore, by the theory, so then the IVP has a solution, yeah? So the IVP has a solution. So IVP stands for initial value problem. Has a unique solution, yeah? And you can verify that, okay? If you remember how to solve this one, it's okay. But if you don't remember, then you can verify that this is the solution. So how do you verify this is the solution? So how do you verify this is a solution? Huh? Just substitute it in. Just plug it in. Yeah? So if you plug it in, then you got dy over dt. It's just 1 plus t plus pi over 4 square, right? So remember the derivative of the tan function, just 1 over x squared, yeah? And this one, sorry, the derivative of tan is secant square, yeah? Sorry, I forgot. This one is tan inverse. It should be 1 plus secant square, right? No, only secant square, sorry. Only secant square, right? Derivative of tan is just secant square. Yeah? And what is secant square? So secant square just 1 plus tan square, right? Yeah? So this one just from trig identity, yeah? And then this one just 1 plus y squared. So that's correct, yeah? So the left equal the right hand side. So therefore it's okay. So that's a solution. And now we have to verify the initial condition as well. So what is y at 0? So y at 0 is just 1 plus tan, just tan at 0 plus pi over 4, which is just tan pi over 4, which is equal 1. So that's correct, yeah? So it is the solution, and it satisfies the initial condition, okay? And if you were curious how to solve this, if you remember first year calculus, then you can solve it exactly as well. So dy over dt equal 1 plus y squared. You can solve it by separation of variable like this. Yeah? And this one gives you tan inverse y equal t plus some constant. It means that y equal tan t plus some constant. Yeah? And then you just put in y equals 0. So y0 equal 1 implies that tan 0 plus c equal 1. So therefore c has to be 5 over 4. So y has to be tan of t 5 over 4. Okay? So but in this case, because you remember calculus, okay? What happens if you don't remember calculus? You have to use Euler method. Yeah? And sometimes, there's a lot of ODEs just non-linear. You cannot solve it exactly. Okay? And it blows up at t go to pi over 4 because, when t go to pi over 4, then this one becomes tan pi over 2, and let's go to infinity. Okay? So now we're interested in numerical solution. So now suppose you have an ODE that's not easy to solve. Yeah? So suppose now we have, so this one will be time again, and this is y. Okay? So now I'm going to discretize it because, in computers, we cannot have a continuous function. We have to discretize it. So suppose I divide it. So this one is T0, T1, T2, and so on, up to Tn. So Tn is when I stop my numerical methods, yeah? And then I have my numerical solution, so numerical approximation. So suppose this is y htn. So suppose, so y at t0 is given, yeah? Okay, so this one is y0 is given because this is the initial condition. But numerically, I might compute y1, yeah? So y1 will be my yh at t1. Okay, so it's a numerical approximation of the exact solution. So this one is y2, and this one is yn, so on. Because I don't know I don't know the exact solution, so I have to compute a numerical solution like this. And you see that if I refine the intervals, I make more points, make it denser and denser. Then eventually I can connect the dot to make a numerical solution. Okay, so your numerical solution is when you just connect all the red dots. So now the question is, how do you find a numerical solution? So, Euler he considered this problem long time ago. I think around the 17th century. I think at that time he was trying to observe some star, and he needed to compute the orbits of some star. I forgot, or some planet. And then he had to solve the ODE, and the ODE is non-linear, so he cannot use any calculus. I don't know whether the calculus was invented at that time or not. But anyway, he couldn't do anything. And then he had to come up with some method to solve the ODE. Okay? And then he came up with Euler method. So what did he do? So I just say that, suppose you consider the ODE like this, yeah? Then, this one you cannot compute exactly, but you can approximate by yt plus h minus yt divided by h. Yeah, so remember this one, the different quotient, because when h go to 0, this one goes to the derivative with respect to time. Okay? And this one you approximate by f dy. Yeah? Then by this formula you have yt plus h. Approximately it is equal yt plus h f dy. Yeah? And now, if suppose I put a uniform partition. So suppose I have t0 equals 0, and t1 equal h, t2 equal 2h, tn equal nh, yeah? Then ytn plus h can be written as ytn plus h f tn yn, yeah? And tn plus h is nothing but y at tn plus 1. Because remember tn is for nh, so tn plus h is n plus 1h for tn plus 1. So equal approximately ytn plus h f tn yn. Yeah? And now, see, because now we don't have exact solution. So now I replace this one by the numerical sequence. So this one becomes yn. So this one is just yn plus 1. And this one is h f tn yn. And this one becomes Euler method. And you can see that by looking at the last formula, suppose you have y0, you can compute y1. You have y1, compute y2, and so on. Yeah, so you have a sequence of y0, y1 up to yn, and then you can connect all the dots, and you have a numerical solution. So another way to look at it is you can look at so in this, I just look at the different quotient approximation of the derivative. But another way to look at it is you can look at the integral version. Suppose you have, so this one way to look at the method, yeah? The other way is, suppose I have dy over dt equal f yt like this, yeah? Then if I integral the equation, then I have just y t1 minus y t0, it's just integral of f from t0 to t1, right? I just integrate this equation. And this one, just s y ds, yeah? And then I move this one to the left, then I have y t1 equal y t0 plus integral t0 t1 f sy ds. Okay? So just another way to look at it. And now, so now, you know, this one is an integral, right? So look like this. So the integral is from t0 to t1. And you can approximate this integral by just taking the quadrature. Yeah, so the quadrature, just use the rectangular rules. Yeah, with the left point. Then this one we approximate by h. Yeah, so remember from here to here, just h. Yeah, time f at t0. So you have something like this. Okay, so what is here? So you approximate this integral by the width multiplied by the height of the rectangle, yeah? And then, you know, I mean from here you can define h1, sorry, define y1, yeah? And if you have y1, you can define y2 and so on. So in the end you have the same formula. Okay? And this is Euler method, so Euler, he came up with this formula in 1768, a long time ago before. I think roughly this at that time calculus was available already, right? I think Newton, he invented calculus maybe 20 years or 40 years before this, and after that Euler just came up with this formula. And you know, I mean, another way, you can look at the Taylor polynomials and then you come up with the same formula. Okay? So now, suppose now I have a simple initial value problem like this. So y prime equal t plus y, yeah? So by calculus, in this case, you can find out what is the correct solution, exact solution. So hopefully you still remember how to solve this, yeah? But if you don't, then there's a true solution here, the exact solution. Then we can compute the numerical approximation using Euler method. So y0 is given because it's initial value. So y0 just equal 1. And then y1, so it's just equal y0 plus h. So this one is f at t0, right? So f at t0 is here. And then from given y1, then you can compute y2 and so on, yeah? And now from the, so in this case, you know the exact value, okay? So y is the exact value in this case because we know the exact value. And yn is just your numerical solution. So 1 here, 1.1 here, 1.22 here, 1.362 here. From this, you can compute the errors. Okay?